I will start with a technical announcement. If it happens that you have comments or questions about this talk and want to share this with me, then if you succeed to connect to the internet, you can go to that address, m.socrative.com, go to that room number, and you will find a space there where you can type your comment and questions. I will receive it and I will do something with that. So you will not send it into empty space, it will be useful. Don't bother to write this down. This message will appear on every slide somewhere at the edge. Density functional theory. It's about 30 years that this method is being applied now to realistic materials. And if you look at the people who were interested in using these density functional theory predictions over the years, these people have changed. 30 years ago, our target audience were theoreticians. Later on, the target audience included also experimental scientists. Nowadays, it's very common to find in one paper experiments and DFT calculations in dialogue with each other. And even later on, nowadays, our audience is shifting more and more to material scientists, people who have ultimately a commercial interest in these results. These are different kind of people, and they ask different kinds of questions. Material scientists are very practical people, and one of the questions they inevitably will ask to you, if you tell them, I can predict something by DFT for your material, one of these questions is, how quickly can you do that, and how accurate will your prediction be? Now, the question about speed is quite straightforward to answer. We all have rough estimates in our heads, but the question about accuracy didn't turn out to be so easy to answer. So at least we couldn't point them to a single paper or a set of reviews where that accuracy question was discussed. And that's a problem. If you can't tell them in an objective, quantitative way what is the error bar on your prediction, they will not take you seriously. That's a moment when a warning light starts flashing. And if that happens in your car, you know what to do. You bring it back to the garage for an engine checkup. If that happens in your favorite field of science, you do the same. You bring these codes and methods back to the test bench and you start asking serious questions about accuracy. And that is basically what we have done. Accuracy, you can find that in several different places. I can distinguish 3 sources of errors, and I will discuss today just one of them. But let's go around the loop and look where deviations between our DFT predictions and experiment can come from. And a major source of errors is what we call the intrinsic errors, the errors that are introduced by guessing your exchange correlation functional. Whatever you do, you can never beat the quality of your functional. Intrinsic errors. There is a paper here where a discussion about these intrinsic errors is made. Don't bother to write that down, you will get the information at the end. But I won't talk about intrinsic errors here today. Second set of errors is what we call the model-related errors. And these are actually the descriptors that were mentioned in the previous talk. Very often you don't calculate the property that the experimental people measure directly, but you calculate a simpler property that by some magical relation can be correlated to the real experimental property. And that as well introduces a series of errors. What I will talk about today is the third class of errors, the numerical errors. And these are the errors that come from all the numerical algorithms that enter in a particular DFT code. You try to solve the Kohn-Sham equations as accurately as you can, but you do that in a numerical way, so inevitably that will introduce some errors. You can compare it to this situation. If you have a computational task, say this simple sum, and you give it to 2 different computational devices, 2 pocket calculators, you hope to get the same result. Well, we do now exactly the same. we have a computational task, a set of benchmark crystals. We give them to two different DFT codes, calculate the same properties, and you hope to get the same result by both codes. What will our benchmark set be? We take a very simple set, all elemental crystals. So for every element of the periodic table, you look what is the ground state crystal, and you do a very accurate DFT calculation by the codes of your choice for all these elemental crystals. As a matter of example, I compare here two codes, VASP and Wien2K, where for one particular element, FCC copper, we calculate an energy versus volume curve. And from that energy versus volume curve, you extract an observable property. For instance, the bulk modulus, the curvature near the minimum. And for these two codes, this gives a number of about 137 gigapascal for VASP and 144 gigapascal for Wien2K. It's not exactly the same number twice. There is a difference, so that is a numerical error. Be sure we have taken care that for both of these calculations, this was done with very, very high numerical accuracy. So whatever you try, the digits you see there will not change anymore. These are the final answers of these two codes. If you are worried that there is quite a large difference between these two, a difference of say 6-7 gigapascal, that's not too much. The error you have by choosing the PBE functional is twice as large. So the noise between two codes is smaller than the noise introduced by the choice of the functional, which is a reassuring observation. Well, that was just the bulk modulus. There is more information in this energy versus volume curve, and we tried to extract all that information at once. So therefore, we introduced a gauge, a measure, which is called delta, and which is the difference in area between these two energy versus volume curves. So you bring them down to the same baseline, superimpose them, and you measure what is the area in between. If both codes would predict exactly the same energy versus volume curve, that quantity would be zero. If there is any deviation of whatever nature, that number will go up. And if you apply that for that FCC copper example, so VASP versus Wien2K gives you a value of 0.5 millielectron volt per atom, which is a small deviation. You can do that not only for FCC copper, you can take these same two codes and compare the entire benchmark set, and you get that kind of periodic table with the delta values for every element. We have collected that information on a website, and I will try to go there, hoping that this internet connection survived. So what do you see here? A set of codes that have been tested so far. Several of the mainstream DFT codes are in there. Several of them appear multiple times, which means that they were tested with different set of pseudopotentials or PAW projectors. And they are ordered according to this delta, which is the average over the periodic table, over the benchmark set of all these individual comparisons. The reference code was Wien2K, so that has by definition a delta of 0, and the other codes are ranked in order of increasing delta. So the smaller this number, the better all these other codes reproduce the Wien2K results. You need to have a feeling for what these numbers mean, and it has taken us some time to get that feeling. But in one sentence, I could say everything that is below 3 in these units are two codes that are for practical purposes identical. So if the line of 3 is about here, everything above this line reproduces for practical purposes the same result. There is more information than just this list. You can click, for instance, one particular entry, and then you get this overview table. So these are all the individual delta values for quantum espresso versus Wien2K. You can do that for any code. If you are interested in just a few elements, let's say you are a semiconductor person and you want to study silicon and germanium that are doped by some elements, then you get the list again, but now with deltas averaged only over these 4 elements. And you see, for instance, a code da capo, which was in the very bottom for the overall list, jumps now up, so it performs much better for these 4 elements than for the entire average. And if you don't like the fact that Wien2k is taken as a reference, there are good reasons to take it as a reference, because that is a method that doesn't need a pseudo-potential. But if you don't like that, if you want to take another code as a reference, then let's take, for instance, Abinit with JTH potentials. You can click that line and it reorders now with this code as the reference and everything else ordered with respect to that code. So you can inspect pairwise correlations. There is a lot of information there, and it's not without a reason that we put that information there. This is actually an invitation to you. You can play with that information and search for trends and correlations. And if you report that back to us, then we will try to summarize all this information and give some general overview of how all these codes behave with respect to each other. There are quite some people involved in this. So we didn't do all these calculations ourselves. We did a few of them, but then we invited people people involved in a lot of other different codes. You see the list here, to run that same benchmark set. And these results are steadily arriving. We expect our list will grow considerably over the next few months. So once that is done, we will have a real comprehensive overview of the performance of all DFT codes with respect to each other. You can wonder, why is that useful? Which is my last slide. Some of the people involved called this more than just a science project. This is almost a social experiment. And that's really one of the unexpected, interesting features of it. By working on the same benchmark with all these different codes, people from all these communities start talking to each other, which was a very useful, unexpected benefit. The practical result is that we will have now quantitative numerical error bars for all of these codes. That's a mutual quality cross-check of all of these codes. So all codes will benefit from this because you can show that you do as good as the others. And that will be the documented proof to our partners in industry and material science that the methods we use are really reliable. So the goal is that we make from all this information a community consensus paper that in high energy physics style will have 50 or more authors, I guess, where we present all this quality comparison once and for all in a quantitative way. It has already led to improvements in individual codes. People have spotted wrongly behaving potentials by this benchmarking. And so codes have already improved, manuals have already improved. So there is really a lot of benefits. So to wrap up, what is the result of our engine checkup? The conclusion is that our engine is really running fine. We knew that, but now we can prove that to others. And the more data you have to prove that, the better. So if you feel like collaborating on this, it's fine that you test your own codes, that you search for correlations on the website, and we'll use that information for sure. You can download the slides and a set of references on this address. If the technical thing went fine, then also the recording of this talk will be available on that address. It will be on YouTube, and where to download it exactly you can find there. Not at this moment, but in 24 hours from now. Thanks for your attention.